Hey guys, welcome to another video of Problem of the Day series, GFG and LeetCode Problem of the Day. So yeah, it's been around 2 to 3 days since I have not put any video of the Problem of the Day series. So if I got a chance, I will create another something like random series in which I will put all the missed questions that I didn't solve and put the video on Problem of the Day series. So yeah. So without any further ado, let's solve the GFG and LeetCode problem today of day uh, third. So the LeetCode problem of the day was word search. So problem statement is given an n cross n grid of characters board and a string word. We have to return true if the word exists in the grid or not. Now the word can be constructed from letter of sequentially adjacent cell where cells are horizontally or vertically neighboring. Okay. The same letter cell may not be used more than once. So the given two conditions are the word can be only formed by horizontally and vertical neighboring uh, adjacent cells, and the same letter cell may not be used. So the if we have used a cell, we will not be using it again. So it is in given example, and in the given example, what we this will be our given board. It will be something like a matrix, and our given word is this. So as you can see, it is present. It is grid A B C C A D A B C C A D. Similarly, in example number two, it is present. Hence, we are returning to. And as you can see, there is no word such as A B C B in this grid. It's A B, then A B C. There is no B, then A. So in this case, we will return false. The constraint provided to us are the m and n will be between 6 and our words total length will be between 15. So this is an indicator that it is a backtracking algorithm, that it will just be a brute force, it will just be recursion. There won't be any solution. There won't be any optimal solution. It will be particular recursion based approach. So yeah, let's solve this problem. So this problem, there will be two steps. The our main step will be our second step. In the first step, what we will do, so in the first step, we have to iterate all the cells of the grid to find out the first column, to find out the first character of word. So suppose let's take the example, and you can see the first character of word is A. So in the cell, in every cell of this grid, every cell of this matrix, we have to find wherever A is present. So, because if we just start from any of the random cell, if we just start from our first cell, uh, if it is not present, if A is not present there, then it will simply return a false. Therefore, we have to traverse to all the cells of the grid. So you can see in this, our first step is to traverse all the grid cells. So it will be from I equal to 1 to n, j to 1 to m, j equal to 0 to m to traverse all the cells of the grid. And our boards of ij, so our board at a particular cell, we will just match if its character of the word first character is similar or not. Our character is a word store two characters. In Java, we got a string. So I just converted it into an arrays of character of words to it so it can be easily accessible. And then we will call each exist function that will traverse all of its existence cell. Now in the given question, it is said that we uh, it will be done through horizontally and vertically, but I didn't read this whole question at in the when I was solving, so I am traversing through all the cells. So you can just solve this question by horizontally and vertically traversing the neighbors. So the second step will be start checking from that cell to all its adjacent cell and to find out if we could find a particular word, if we could find this particular word or not. Okay, so let's take this example. So as we will first do a traversal on all the grid and check for our first character which is present at particular cell. So let's suppose we are presented this character. So let's not take this example. Let's suppose we are presented this character. Let's take this for example. We are presented this character. Now it will traverse to it horizontally and vertically. Or let's take an example as it travels to all the adjacent cell. Okay. So first it will go above, and then it will go towards this cell. It will go toward this cell, and it will go towards down. Now, if, as you can see, it's down and it's on the left. It is going outside the borders of the matrix, so it will simply return a false. So this will give a false, and this will give a false. Now, in this case above, as you can see, we will also have a word length, word array with us, which will be having all the words. And then we will have a variable k which will give do on each match it will we will have a recursive call and we will do a k plus one. So what it will do our k we point to now our k in this case our k points here. So as our k points here it will check if our s is equal to this b or not. In this case our s is not equal to b so it will simply return a false here. Now, similarly, it will also be a k plus 1 matrix. So in this case, our k is not equal to b, so it will also return a false. And then this will return a false to our main function, indicating that we didn't find any word. So let's take it as our original example, and let's have a k with us. Now k is at 0. Now we have traversed through all the cells, and we have found the a here. So our k will be 0. Now, as you have say, as our A0, it will traverse to this cell, it will traverse to this cell, it will traverse to this cell, and they all three of them return false here. Now it will traverse to this cell, and now a K is one. So it will so this cell data will be checked with this K. Since the both are equal, it will be traversing through its the adjacent cell, which will be this one, then this one. It will also go is towards it backward, and it will go towards it forward. Now, in the backward, what we will do, uh, have to somehow make sure that it both towers the cell that is coming from. So either we will have a visitor array, which will check if that cell is already visited or not, or we will make some changes in this grid by having some character indicating that it is already visited. So in my case, I will enter a hashtag here, indicating that it is already visited. So if it founds it is a hashtag, then it will return a false here. Now it will go towards this case. And now our k is 2. Now our k is 2. Now as our k is 2, now so it will check its C to this data. Now it did found out they both are similar. So it will go towards backward, upward, or this and this cell. And similarly, this will return false, this will return false, and this will return false. It will check to itself. Now k is 3. It will see if C and C are equal. It will go toward this cell, this cell, this cell, and this cell. Now, as you can see that now our K will be 4. So F and E are not equal, so it will return false. S and E are not return false. It will go toward this cell. As you can see that E and E are equal, so we will have a call from here to here, and then here and here. So as you can see, our D and E are not equal, it will return a false. It will return a false because it is already visited. It will return a false because it out of boundaries. And then our it is a D. So they will both will be matched, and we will have a base case indicating that we have reached uh, k equal to words dot length. So if we our k, which will be in this case our we will do k plus one. So in this case 1, 2, 3, 4, 5, 6. Now if our k is 6 is equal to words dot length, then it is indicating that we have traversed all the words character. And hence in this case we will return a false. So this will return false to this will return a false, and this will traverse and then this will get a false here. And this will sorry, this will return a true here, and then till this it will be uh, this will shall will get a true, and it will return a true to its main function, indicating that we did find out a word in the grid. So this okay, so let's go to our code. So this code does the thing. Uh, and this condition will check if we have traversed all the words character, means our k is equal to words dot length, which will return true. Now this will check for the boundaries condition and the visited condition. Now in this case, if I is lesser than 0, j is lesser than 0, I greater than equal to n, and j greater than, we could check for the boundaries condition. And this condition check if our board uh, a certain grid character and our word character are similar or not. If they are not similar, then it will simply return a false. Now, it has passed this condition, means it is a safe grid to traverse, means the grid cell and our kth word at k and our kth character in word is similar. They both are similar. So we will simply do a board of I is equal to hashtag indicating that we have visited. Then we have a if condition that will traverse to all of its adjacent cells. That will do is that it is exist board word I plus one j k plus one and m. I minus one, so I plus one will be for the downward direction. I minus one will be for upward direction. Then I j minus one will be to go toward his left side, and I and j plus one to go toward his right side, and k plus 1 indicating for checking to its next word character. And if any of these returns are true, then we will simply return a true to indicating that we did find out that word. And if they all return false, we will come here and uh, do and at k in the particular grid cell we have a hashtag that we simply replace for whichever character was already present at that. So it will be word of key. And then we return a false, indicating that we didn't find any answer. Now, if these both conditions are true, we will return a true that a word was found out, and if not, we will return a false. Now, the time complexity of this approach is as we are in this case, we are traversing all the cell grid, so it is big of n into m. Now, this exist function is will traverse all the grid characters just once. Because we are having a condition that if it is visited, then mark is at hashtag, indicating that we have visited this cell. So in the and this also functions, which is a recursive call, is just making a call to its adjacent cell. So it will be just once. So the time complexity of this approach is big of this first one will big of. Okay, let me write it here. This first one will be bigger of n into m, and this function is bigger of m into n. So the total time complexity of this approach will be big of n square into m square. Um, so yeah, this will be time complexity. Space complexity will be nothing as we are not using any of the extra space. You can also consider time complexity as big of n into m because we are having a call stack here which is doing all the recursive call. So you could also just say that in the interview we are using a stack to we are using a stack to store all the recursive call, hence the space complexity is also big of n into n. So this will be it for this problem. Let's move toward our GFG problem. So the problem is create and common ancestor in binary search tree. So it is a modification of lowest common ancestor. The problem statement is given a binary search tree with n greater than or equal to 2 nodes. So there will always be two nodes present in this tree. We have to find the kth common ancestor of node x and y in the given tree. We have to return -1 if the ancestor does not exist. Now the nodes x and y will always be present in the input of binary search tree and x is not equal to y. So x and y will always be present and x will never be y. Now uh, now you can see that it is a binary search tree. So what are the properties of binary search tree? Um, Duplicates are not allowed in binary search tree. The binary search tree at root node will have greater value than its left node and will always have a lesser than value than its right node. So we can use these conditions that will be useful in our problem. As it is given, it will be a binary search tree, and x and y will always be present. So as you can see in this example number one, we have our KS2. So we have to find the second common ancestor of both the nodes and XS40 and our Y60. And so we can say XS40 and our Y60. So the lowest common ancestor of this 40 and 60 is 50. Now, so what is the lowest common ancestor? So lowest common ancestor is a shared node between given two nodes. Lowest shared node. Consider it as lowest shared node of the both two given node. So for 40, you can see that for 40 and for 60, the lowest common ancestor is 50. This is the lowest shared node of both 40 and 60. Now for 40 and 30, it will be, sorry, for 40 and 20, it will be 30. As 30 is shared by both 40 and 20, and it is the lowest. So this is the lowest common ancestor of both of them. There will be a case where given two nodes are 50 and 20 and 40. So in this case, the lowest common ancestor will be 50 as 50 node uh, 50, as 40 is shared by 50. As 40 is a parent of sorry if as 50 is parent of 40. So lowest common ancestor will be 50 in this case. Now the 40 and 50 sorry 40 and 60 the lowest common ancestor is 60. So this will be our first uh, ancestor, first common ancestor. Our second common ancestor will be this 30 in this case. Now, in the example number two, it is -1 because the two given nodes are 40 and 60. Its lowest common ancestor will be 50. And so, in this case, the root node is first ancestor of both these nodes. So, there is no parent of this. So, there will be no ancestor. So, and there will be no second common ancestor. Hence, we are returning a -1 in this case. The time the n and k are given between 1 and 10 raised to 5. Okay, let's go toward this explanation. So this problem, the kth common ancestor, consists of two problems. The first problem is lowest common ancestor, as I already told you, and the second problem is get path. So I will come toward the get part, why we need to find the path. So the first thing will be to find out the lowest common ancestor of particular node. So to find the lowest common ancestor, the process will be as we are given two. Let's consider two nodes as 60 and 40. So our x will be 40 and our y will be 60. So this so we will make a recursive call for its root node, which will be 30. Its 30 will go to its left child, which will be 20. Now its 20 will move toward its left and right child. Now, as you can see, its left and right child are both are null, so hence they will both return a null to it. So this marks as our so okay. So let's now go toward the condition first. As these are both as marked as null, so it indicates that there is no node which is equal to x and y data. Hence, we will not return. So, as both are null, hence we won't make a won't make a decision here that this node is our common ancestor, and hence it will simply return a null to this side. Hence it returns a null. Now it will move towards right its right child. Its right child will move towards its left child. Now first it move towards its null. So it will return a null here. It will return a null here. Now in this case, as you can see, our x is equal to for this node. Our x data is equal to this data. Now, so this will be a condition where we its left and right child is null, but the data present at the root node and data in x is equal. So hence we will return a root node here which is 40. So we will return a 40 here. Now it will move toward its right child. It will return so they both will return a null. Simply as you can see that our y is 60 and our root data is also 60. Hence we will return a 60 here. Now this marks our first condition. So as you can see, this marks our first condition. If left is not equal to null and right is not equal to null, then we will return a zero. So as you can see, our left and right, we have found both our x value and y value. So at present, we are getting both x and y value, and hence I'm sure that the node that we are presented is our shared lowest common ancestor, and hence we will return that node. So we will return a 50 years. So we return a root, as you can see in the condition. So we are getting a 50 year. Now to find the lowest score, now you can see in this we are getting a null, and here we are getting from this left child we are getting a null, and from its right child we are getting a 30, 50. So this marks our third condition, as you can see. Simply we will check if our left is not equal to null. Our if our left is not equal to null, then we are sure that we have a lowest common ancestor which is coming to this node. So we will simply return that node. And in our fourth condition, if our left is not equal to null, if our left is null and our right is having a value, then we will return a right here. Now, okay. So let's now go to the second condition. Let me just erase all of this. Now the second condition indicates that if at certain point, now as you can see that we have traversed this node, its left child and its right child are giving a null to it. Now its both left and right child are having a null, so it won't pass this condition. But here our data, root data, and our x is equal, means this condition is satisfying. So hence we have found a node which stores the value of x, or in this case we are traversing 60, means we have found a node which stores a 60 here, which stores a y there, hence we return a root node. So this marks all our four conditions that why we are using this four condition. So let's go toward the code of lowest common ancestor. We will so this is a function ancestor node which takes root x and y. Now, if the root is equal to null, then we simply return null. Then I'm initializing two variable left and right, which currently stores null. Then I am calling ancestor node for its left child and for its right child. Now, these are the four conditions. If our left and right are not null, then we will return root. Uh, we are because in this case we are sure that this is our shared node because its left child and right child are having some value that is x and y. Now our second condition is else if root dot data equal to x or root dot data equal to y. in this case, we are sure that we have found a X and Y node. Now, this fourth and fifth condition indicates that if our left is null or right is null. So, in this case, we will return if left is not null, then we return left. Right is not null, then we will. If our for right there is no condition. If it is null, we simply return null. If it stores a node, it will simply return a node. So this is our lowest common ancestor function. Now now let's move forward to our second part where we need to find the uh, path. Now, so why do we need to find the path is, as you can see, we are finding out the node of the lowest common ancestor. So this is the path of the lowest common ancestor. What do we need is the kth common ancestor. So we have to find the path to find the kth common ancestor. Why do we need to find this path? Is our this will be our first common ancestor. This will be our second common ancestor. There will be a certain node which is our third common ancestor. There will be a certain node like here, which will be our fourth common ancestor. So we in lowest common ancestor, we are just receiving this node. We have to find out the k common ancestor. Hence, therefore, we have to find its path. So in this case, what we will do, we will have a list or we will have a array where we will store this path. So to store this path, what will be the code will be? So we will first traverse. We will first we will there will be a condition. There will be a function find path which will take this whole tree. Then and also it will take it this node which is the lowest common ancestor. So first our array, as we pass into this function, we will store a 30 in our array list, or we will 30 in our array. So because it 30 is in our path, or the root node will always be in our path. Then as it is now, here comes the binary search tree properties. Now as this is our binary search tree, and we have a root node 50, so our 30 is lesser than 50. So we are sure that we have to just traverse the right subtree to find out the path. We can we can just not traverse the left part because the node we currently that we have, the lowest common ancestor that we have is greater than our root node. So there is no need to traverse to its left part. So our array will 30 and check if our root node is greater than our root node is greater than our ancestor node. If it is not, it will move toward its right path. Now in the second part, it will store a 50 year. Let me just write it. Now you can see we have just reached a node that we have passed in our function. So in this case, we will just simply return. Now this will just simply return and will move out of this. We move outward of this function. So in this way, we will find out our path. So let's take another also an example. If the path consists of six, if this is our past, or this is our, so let's not take this. Let's consider a case where this will be our path. Now, first it will go to 30. Now it will check if 30 is greater than 40. No, 30 is not greater than 40. Then it move add 30 to our array list and it will move toward this 50. Now it will check is 50 greater than 40. No, 50 is not greater than 40. Then we don't have to move toward its right subtree. We have to move toward its left subtree. So it will move toward its this. First it will store 50. Then it will store 40 and it will store 40 and in this check it will check if our 40 is equal to if our node is equal to root node. Yes, it is equal. Hence it will simply return here and it will simply return here to our 30 and it will simply return to our main call. So in this way we could find out our path. So as you can see, if we have to find the uh, second common ancestor in this case. So in this case, what is our second common ancestor? Our second common ancestor will be this array size, which is 3 minus 2, which is our k. So 3 minus 2 is 1. So our second common ancestor will be 0. You can see 0, 1, and 2. So it will be this one. So our second common ancestor will be this 50. So as you can see, this is the second. This will be our first common ancestor, and this will be our second common ancestor. So then now let's move towards our initial example. So our 30 and 50 were our given path, and our 40 and 60 were our nodes. So in this case, we have to find the second common ancestor. So as you can see, the size is 2 minus our k is 2, which gives us 0. So in this case, it will be our second common ancestor. Now there might be a case where our k exceeds the limit of our array list. Means it the path size is lesser than our k. It let us to find us some 80 and 70 kth ancestor node, and we just have 50 ancestor node. So in this case, we will return a minus one if our k is lesser than the array list of size. So here's the code of this function. So we have to initialize a array list here, which will store the path. Then a find path function which takes ancestor, the node that we have LCF ancestor, then the root node and our array list. Now this will be the function. The first it will just add the root node to our node array list. Then it will check if our ancestor node is equal to our root node. If it is, then it will return. Then in the next condition, it will check if our ancestor data is greater than root data. If it is greater, then it will move toward its right side, and if not, it will move toward its left side. And hence, we in this way we could find out our path. Now, the this condition will check if our k is greater than root dot size. If yes, it will return minus one, and if not, it will we will return our kit ancestor node data. So this will get us our kit ancestor node. So to talk about the time complexity of this overall function, so time complexity is big of n as we are traversing. So as this ancestor node is traversing all of its value, all of the tree value, and the space complexity is the big of uh, space complexity is big of height of the tree because we won't store all the data. So we won't store all the value. We will just store some value which is equal to the height. So we are storing 30, 50. In some case we can store 40. So in this case we are not storing all the value. So time complexity is big of all the nodes. Let's say big of and our space complexity is big of height of tree. So this will be it for the this video. I hope you did understand how to solve this problem or how to approach this kind of problems. So this will be it for this video. Uh, I hope you did understood this. Thank you.